Beyond the edge of our solar system, beyond the realm where planets orbit and comets drift, there exists a distance so vast that even light itself must travel for years to cross it. Tonight, we turn our attention to what should be our closest neighbor, a star system so near in cosmic terms that it has captured human imagination for generations. Yet, Alpha Centauri presents us with a beautiful paradox. It is the nearest stellar system to our Sun, and yet it remains so impossibly far that every attempt to comprehend the distance reveals just how small we truly are and how grand the universe has always been. When we look up at the night sky and see Alpha Centauri glowing softly above the southern horizon, we are not seeing a star as it is, but as it was over 4 years ago. The light that reaches your eyes tonight began its journey before the last presidential election, before countless sunrises and sunsets, before memories you now hold dear were even formed. This is not distance measured in miles or kilometers. This is distance measured in time itself, carved into the fabric of space, waiting patiently for us to understand what it means to reach beyond our solar cradle. How long would it truly take to travel to Alpha Centauri? Not in theory, but with real spacecraft, real physics, real human lifetimes stretched against the darkness. What would the journey feel like as decades passed, as Earth became a pale dot, then vanished entirely into the scatter of stars behind you? And if we could somehow arrive, what would we find? What secrets lie in a triple star system where 3 suns dance around one another, where planets might circle in orbits so strange they defy our earthbound intuition? Tonight, we will drift across the incomprehensible gulf between our Sun and Alpha Centauri, exploring not just the distance itself, but what that distance truly means. We will build scale models that stretch across continents, compare journey times that span generations, and discover why the closest star is, in many ways, as unreachable as the edge of the observable universe. We will trace the pathways of our fastest spacecraft, examine audacious dreams of laser-push sails traveling at fractions of light speed, and stand, if only in imagination, on a world orbiting Proxima Centauri, where Earth appears as nothing more than a faint glimmer lost in the glare of our distant Sun. This journey will require patience and wonder in equal measure. The scales we encounter will bend intuition until it breaks. Numbers will grow so large they lose meaning, then regain it only through comparison, through metaphor, through the slow realization that the universe has always been teaching us humility. If this journey resonates with you, if you find yourself drawn to these questions of distance and time and cosmic perspective, please take a moment to like this video and subscribe. Your support allows us to continue exploring these quiet corners of wonder together. And I'm curious, where are you right now as you listen to these words? What time is it where you are? Are you drifting towards sleep beneath a canopy of stars? Or perhaps watching from a city where the night sky has been dimmed by light? Leave a comment and let me know. There's something deeply human about sharing these moments of cosmic reflection, no matter where we find ourselves on this turning world. Now let us begin. Let us shed the familiar and venture outward, not with engines or fuel, but with imagination as our only vessel. Let us trace the silent path to Alpha Centauri and discover what it truly means to reach for the nearest star. The journey is longer than lifetimes, but understanding it, truly grasping what that distance represents, takes only the willingness to look upward and ask, how far is far? Beyond the edges of our solar system, beyond the realm where sunlight fades into the cosmic night, there exists a stellar family so close to us that ancient civilizations gazed upon it without knowing what secrets it held. Alpha Centauri is not a single star, but a trinity, a gravitational ballet of three suns bound together by invisible threads of gravity, performing a dance that has lasted for billions of years. To understand the true scale of Alpha Centauri, we must first understand what we are looking at. This is not merely our closest stellar neighbour. It is an entire system, a miniature cosmos unto itself, where three stars orbit, influence, and illuminate one another in patterns so complex they require computers to fully calculate. The brightest member of this trinity is Alpha Centauri A, a star so similar to our own Sun that if we could replace Sol with it, few on Earth would notice the difference. It shines with a warm golden light, slightly larger and brighter than the star we orbit, a beacon that hints at what our own Sun might become as it ages. Its companion, Alpha Centauri B, orbits alongside it, completing a cosmic waltz that takes nearly 80 years to complete. This star is smaller, cooler, more orange in hue, yet still familiar enough that life, if it exists there, might bask in light, not unlike our own. Together, these two stars form what astronomers call a binary system, locked in eternal orbit around their common centre of mass. At their closest approach, they pass within 11 astronomical units of each other, roughly the distance from our Sun to Saturn. At their farthest, they drift apart to nearly 36 astronomical units, a distance greater than Neptune's orbit. Imagine two suns in Earth's sky, sometimes appearing as brilliant companions, other times separated by vast gulfs of space, each casting double shadows across hypothetical worlds below. But the Alpha Centauri system holds a third secret, one that remained hidden until relatively recently. Orbiting far beyond the binary pair, separated by a distance so great it seems almost disconnected, is Proxima Centauri. This dim red dwarf, the faintest of the three, is also the closest star to Earth. At just 4.24 light-years away, Proxima is our nearest stellar neighbour, though it circles its two brighter siblings at a distance of roughly 13,000 astronomical units, a gulf so vast that it takes Proxima more than 500,000 years to complete a single orbit around the central pair. Proxima Centauri is small, perhaps only 1/7 the diameter of our Sun, and cool enough that its surface temperature gives it a deep crimson glow. If you stood on a planet orbiting Proxima, the star would not appear as a brilliant white disk like our Sun, but as a large, sullen ember casting a strange twilight across the landscape. Yet despite its diminutive size, Proxima is volatile, erupting with powerful stellar flares that can double its brightness in moments, bathing its planets in radiation that could strip away atmospheres or, paradoxically, provide the energy chemistry needs to spark life. The orbital dance between these three stars is not a simple pattern. Alpha Centauri A and B sweep around each other in elegant ellipses, their paths crossing and diverging like figure skaters on cosmic ice. Meanwhile, Proxima traces an enormous, elongated orbit around them both, so distant and so slow that astronomers once debated whether it was truly bound to the system at all, or merely passing through on a journey that would eventually carry it away into the darkness. Recent measurements suggest Proxima is indeed gravitationally bound, though loosely, tethered to its companions by threads of gravity so faint they could be severed by a close encounter with another star. From Earth, the Alpha Centauri system appears as a single point of light to the naked eye, the third brightest star visible in the southern hemisphere. Ancient civilizations saw it and wove it into their myths and navigation charts. The Aboriginal peoples of Australia observed it for tens of thousands of years, incorporating it into their stories of creation and the heavens. Greek astronomers catalogued it, though they could not know what it truly was, It was not until the early 18th century that astronomers realized this brilliant point was actually two stars orbiting each other, and not until 1915 that Proxima Centauri was discovered, a faint red companion so dim it requires a telescope to see. What makes the Alpha Centauri system so special is not just its proximity, but its familiarity. In a galaxy filled with exotic stellar phenomena, pulsars, neutron stars, black holes, and supergiants, Alpha Centauri offers something rare, stars that resemble our own. Alpha Centauri A is nearly a mirror of the Sun, suggesting that if planets exist there, they might orbit in conditions remarkably similar to those that gave rise to life on Earth. The presence of 3 stars means 3 separate habitable zones. 3 chances for worlds to form in regions where liquid water could exist, where atmospheres could be stable, where life might take hold. Astronomers have long wondered whether planets orbit within this system. For decades, the question remained unanswered. The gravitational chaos of multiple stars can disrupt planet formation, scattering material before it has a chance to coalesce, or flinging young worlds into unstable orbits that send them spiraling into their suns or ejecting them into interstellar space. Yet recent discoveries suggest that planets can and do form in such systems. Around Proxima Centauri, at least 2 planets have been detected, including one that orbits within the star's habitable zone. The possibility that worlds exist around Alpha Centauri A or B remains tantalizingly open, though no definitive discoveries have been made yet. To observe the Alpha Centauri system from space would be to witness something no human eye has ever seen. If we could travel there, not in thought but in body, and look back toward our own sun, we would see Sol as it truly is, a single, unremarkable yellow star among billions. From Alpha Centauri, our sun would shine in the constellation Cassiopeia, bright enough to be visible, but no longer the center of all things. It would be humbling, a reminder that our solar system is not unique, merely one among countless others. The Alpha Centauri system forces us to confront the nature of distance in ways that numbers alone cannot convey. These stars are our neighbors, the closest suns beyond our own, yet they are separated from us by a void so immense that light, the fastest thing in the universe, takes more than 4 years to cross it. No human has ever traveled even a fraction of that distance. No spacecraft we have built could reach Alpha Centauri within a human lifetime using current technology. Yet it is there, glowing in the southern sky, a reminder that other suns exist, other worlds may orbit them, and perhaps other eyes look back toward us across the darkness. The history of Alpha Centauri is written not just in light, but in time. The photons we see tonight left those stars during the year 2020, carrying news of distant suns across the interstellar void. By the time we invent the means to travel there, those stars will have moved, their orbits shifted, their light changed by the passage of years we can scarcely imagine. This is the Alpha Centauri system, a stellar trinity bound by gravity, separated by unimaginable distances, and yet closer to us than any other star. It is a destination that challenges our understanding of scale, time, and possibility. And it is the next chapter in our journey to comprehend the true vastness of the cosmos. We speak of light years with casual ease, as though the term itself explains the distance. But pause for a moment and consider, what does it truly mean to travel 4.37 light years? This number, so simple in appearance, conceals a distance so vast that our minds struggle to hold it, even as we attempt to break it down into comprehensible pieces. A light year is not a measurement of time, though the name suggests otherwise. It is a measurement of distance, the distance light travels in 1 Earth year. And light is fast, incomprehensibly fast. In a single second, light crosses 299,792 kilometers, nearly 186,282 miles. In that same second, light could circle Earth's equator more than 7 times. By the time you finish reading this sentence, light has already traveled from the Earth to the Moon and back. Yet even at this breathtaking velocity, light takes time to traverse the cosmos. The light from our Sun requires 8 minutes and 20 seconds to reach Earth. When we gaze at the Sun, we are not seeing it as it is now, but as it was 8 minutes ago. We are looking backward through time, observing ancient photons that began their journey before we thought to look up. Now extend that journey, not 8 minutes, but an entire year. 365 days of continuous travel at light speed. The result is 1 light year, a distance of approximately 9.46 trillion kilometers, or about 5.88 trillion miles. It is a number so large that it loses meaning the moment we write it down. Our brains, evolved to comprehend distances measured in footsteps and horizons, cannot grasp the scale of trillions without translation. So, let us translate. Alpha Centauri lies 4.37 light-years away. Multiply that single light-year by 4.37, and we arrive at roughly 41.3 trillion kilometers, or 25.7 trillion miles. To put this into perspective, consider the distance from Earth to our Moon, approximately 384,400 kilometers. We could travel to the Moon and back more than 53 million times before covering the distance to Alpha Centauri. The Apollo astronauts, humanity's farthest travelers beyond low Earth orbit, journeyed to the Moon in about 3 days. At that same speed, reaching Alpha Centauri would require more than 870,000 years. Perhaps the Moon is too close for comparison. Let us consider instead the distance from Earth to the Sun, our astronomical unit, or AU. 1 AU equals roughly 150 million kilometers. It is the baseline by which we measure our solar system, the fundamental yardstick of planetary distance. From Earth to Alpha Centauri spans approximately 276,000 astronomical units. If we could compress the distance from Earth to the Sun into a single meter, Alpha Centauri would still lie 276 kilometers away, the distance of a long drive through unfamiliar countryside. These numbers pile upon one another, each comparison revealing not clarity, but deeper mystery. Why is it so difficult to comprehend? The answer lies not in mathematics, but in biology. The human brain evolved to navigate environments measured in kilometers, not trillions of them. Our ancestors needed to estimate distances between trees, between camps, between visible landmarks. Natural selection favored minds that could judge whether a river was crossable or whether a predator was close enough to pose danger. There was no evolutionary pressure to comprehend interstellar voids. And so we encounter a cognitive wall. Beyond a certain threshold, numbers cease to feel different from one another. 1 million, 1 billion, 1 trillion. They blur together into a single abstract category, unimaginably large. We understand that 41 trillion is greater than 1 trillion, but we do not feel the difference. Our intuition collapses under the weight of zeros. Light itself becomes our guide through this incomprehensible expanse. It is the universe's absolute speed limit, the fastest anything can travel, according to the laws of physics as we currently understand them. Nothing with mass can reach light speed. As an object accelerates closer and closer to this cosmic boundary, strange things begin to happen. Time dilates, mass increases, energy requirements approach infinity. The universe itself seems to conspire against faster-than-light travel, enforcing a fundamental constraint on how quickly information, matter, or energy can move through space. This speed limit is not arbitrary. It emerges from the structure of space-time itself, woven into the fabric of reality by Einstein's theory of relativity. Light travels at this speed not because it is trying to go fast, but because it has no mass. Photons exist in a state of perpetual motion, unable to slow down, forever racing through the vacuum at exactly 299,792 kilometers per second. To travel at light speed is to experience no passage of time at all. From a photon's perspective, if such a perspective could exist, the journey from Alpha Centauri to Earth is instantaneous, beginning and ending in the same eternal moment. But we are not photons. We are made of matter, bound by mass and inertia. For us, 4.37 light-years represents not an instant but an epoch. Even travelling at a significant fraction of light speed, say 10%, the journey to Alpha Centauri would require more than 43 years. At 50%, it would still take nearly 9 years, and achieving such velocity would demand energy resources beyond anything our civilization currently possesses. Consider for a moment the spacecraft Voyager 1, humanity's most distant ambassador, launched in 1977 and now travelling through interstellar space. It moves at roughly 17 kilometers per second, faster than any human-made object has travelled for such a sustained duration. Yet, at this impressive velocity, Voyager 1 would need more than 73,000 years to reach Alpha Centauri if it were headed in that direction, which it is not. The stars are so far apart that even our fastest machines are barely crawling through the cosmic ocean. These numbers force us to reconsider what distance means. On Earth, distance is something we overcome routinely. We drive across cities, fly across oceans, traverse continents in hours. Distance is a temporary obstacle, solved by technology and patience. But interstellar distance is different. It is not merely far, it is fundamentally alienating. It separates us not just by space, but by time, isolating star systems from one another in a way that challenges our deepest assumptions about travel and connection. And yet, 4.37 light-years is close. Alpha Centauri is our nearest stellar neighbour, practically on our doorstep by galactic standards. The Milky Way galaxy spans roughly 100,000 light-years from edge to edge. The nearest large galaxy, Andromeda, lies 2.5 million light-years away. Compared to these distances, Alpha Centauri is intimate, almost touchable. Perhaps that is the strangest realization of all. This impossible distance, this 41 trillion kilometer gulf that defeats our intuition and dwarfs our fastest spacecraft, represents the closest another star can possibly be. If we cannot easily imagine reaching Alpha Centauri, how can we hope to comprehend the true scale of the universe beyond? The answer may be that we cannot. Not fully. Not in the visceral, intuitive way we understand the distances of our daily lives. But we can try. We can build metaphors, construct models, and translate cosmic distances into familiar terms. We can let the numbers wash over us, not seeking to grasp them entirely, but allowing them to reshape our sense of scale gradually, patiently. Understanding 4.37 light-years is not about memorizing a number, it is about confronting the vastness of space and emerging with a deeper sense of humility and wonder. It is about recognizing that the universe operates on scales so grand that our comprehension will always be incomplete, and finding beauty in that incompleteness. As we continue this journey toward Alpha Centauri, the numbers will remain staggering. But perhaps, in time, we will learn to sit with the incomprehensible, to let it teach us that some distances are meant not to be conquered, but contemplated. The human mind is extraordinary, capable of imagining cities we've never seen, creatures that never existed, futures that have yet to unfold. But when confronted with the distance to Alpha Centauri, our imagination falters. Numbers alone cannot capture the scale. 4.37 light-years stretches beyond intuition, beyond visualization, beyond any frame of reference evolution has equipped us with. So we turn to models, analogies, and thought experiments, attempting to shrink the cosmos down to something we can hold in our minds, even if only for a moment. Let us begin with a familiar image. Picture the sun, not as an incomprehensible ball of nuclear fusion 865,000 miles across, but as a beach ball about 2 feet in diameter, resting on a sandy shore in Los Angeles. If the sun is a beach ball, then the Earth becomes a small peppercorn, orbiting at a distance of about 215 feet away. Mars, a slightly smaller grain, sits roughly 330 feet from our beach ball sun. Neptune, the outermost planet in our solar system, would be positioned nearly 1.5 miles away, a tiny marble barely visible in the distance. Now comes the moment of reckoning. If we maintain this scale, where would Alpha Centauri be? Not in the next city, not in the neighboring state. Alpha Centauri, our closest stellar neighbor, would be another beach ball positioned in Tokyo, Japan, over 5,500 miles away. That is the true scale of interstellar distance. Even when we compress our entire solar system to the size of a neighborhood, the nearest star system remains on the opposite side of the planet. This visualization is humbling, but it is also liberating. It reminds us that the distances between stars are not merely vast. They represent a different order of reality altogether, a scale so immense that our everyday language struggles to articulate it. The space between stars is not empty distance. It is a cosmic ocean, and we are standing on the shore, contemplating a voyage to another continent we cannot yet see. Another way to grasp this distance is through the marble and football field analogy, one that astronomers often use when teaching students about the structure of the universe. Imagine placing a marble at one end of a football field. This marble represents the sun. At the opposite end, 100 yards away, place another marble. This is Alpha Centauri. Between them, the football field stretches long and empty, a metaphor for the interstellar void. But here is where the analogy becomes even more striking. On this scale, Earth is not even a grain of sand. It is microscopic, a mote of dust circling the first marble, so small it would be invisible to the naked eye. If we were to place our solar system's planets on this field, they would all be clustered within the first few inches around that marble. Neptune, the farthest planet, would sit less than 4 inches away from the sun. Everything we know, every mission we have ever launched, every planet we have studied, exists within that tiny radius. The rest of the football field remains untouched, unexplored, a testament to the staggering distances that separate even neighboring star systems. But perhaps numbers and models still feel too abstract. Let us turn instead to time, a dimension we understand more intuitively. Suppose you decided to walk to Alpha Centauri, not through space, but along a path stretched across the void, walking at a steady pace of 3 miles per hour, 24 hours a day without rest, it would take you more than 100 million years to arrive. Entire species would evolve and go extinct while you walked. Continents would drift. Mountains would rise and erode to dust. If walking feels too slow, consider driving. At highway speeds of 60 miles per hour, the journey would still take over 50 million years. Even if you could somehow maintain this speed through the vacuum of space, you would pass through eras of geological time, epochs beyond human comprehension, before glimpsing the light of Alpha Centauri growing brighter in the windshield. And what about flying? Commercial jets cruise at roughly 500 miles per hour. At this speed, the journey would take approximately 6 million years. To put this in perspective, 6 million years ago, our ancestors had not yet stood upright. The first humans, Homo sapiens, would not appear for another 5.7 million years. You would depart in an age of ancient primates and arrive in an era unimaginable to those who began the journey. These comparisons are not meant to discourage. They are invitations to wonder. They ask us to confront the universe as it truly is, not as we wish it to be. And in doing so, they reveal something profound. The cosmos operates on scales that dwarf our existence, yet we are capable of understanding them, measuring them, and even dreaming of crossing them. Astronomers and educators have developed numerous thought experiments to help students and the curious public grasp these distances. One popular exercise is to shrink the solar system down to a scale where the entire orbit of Neptune fits within a single city. If Neptune's orbit were reduced to a circle with a 1-mile radius, the Sun would be the size of a small coin at the center. On this scale, Alpha Centauri would still be over 4,000 miles away, roughly the distance from New York to London. Another approach involves compressing time itself. If the entire history of the universe, from the Big Bang to the present day, were condensed into a single year, the Sun and Earth would have formed in early September. Complex life would not appear until mid-November. Dinosaurs would rule for a few days in late December, and all of recorded human history would flash by in the final seconds before midnight on New Year's Eve. On this timescale, a journey to Alpha Centauri at our current spacecraft speeds would take not years or decades, but the equivalent of several months within this compressed calendar. Time itself becomes a ruler by which we measure the impossible. Yet even these models, elegant and instructive as they are, fall short of true comprehension. There is something irreducible about interstellar distance, something that resists all attempts at analogy. We can shrink the universe, compress time, transform stars into marbles and planets into dust, but the essential truth remains. The space between stars is so vast that it challenges the very architecture of human thought. Perhaps this is why astronomers often speak of interstellar distances with a mixture of awe and resignation. They know the numbers, they understand the physics, but even they admit that true intuition for these scales does not come easily. It must be built slowly, layer by layer, through years of study and contemplation. The cosmos does not reveal itself all at once. It unfolds gradually, like a story told over lifetimes. Interactive models have become valuable tools in this pursuit. Planetariums and science museums now offer virtual journeys through space, allowing visitors to experience the sensation of traveling outward from Earth, past the Moon, through the solar system, and into the interstellar medium. These experiences use motion, sound, and visual cues to convey scale in ways that static images cannot. As the simulated spacecraft accelerates, planets shrink to points of light, the sun dims to a distant star, and the vast emptiness of space becomes not just a concept, but a felt reality. These models work not because they make the distance smaller, but because they invite us to sit with the vastness, to let it wash over us without rushing to comprehension. They teach us that some truths are best understood, not through perfect analogies, but through patient, sustained attention. Alpha Centauri is far, impossibly far, and yet it is there, waiting in the darkness, a destination that beckons not because it is easy to reach, but because it represents the horizon of what we might one day become. As we leave behind these thought experiments and return to the reality of interstellar space, we carry with us a new perspective. The distance to Alpha Centauri is not a barrier. It is an invitation to think differently, to dream larger, and to recognize that understanding the universe requires not just knowledge, but humility in the face of its immensity. Beyond Saturn, beyond Neptune, beyond the farthest reaches of our sun's influence, there exists a space so profoundly empty that it challenges our very concept of nothingness. To journey toward Alpha Centauri is not simply to travel through darkness. It is to enter a realm where matter itself becomes a distant memory, where the distance between atoms stretches farther than entire cities, and where silence takes on a depth that no earthly experience can approximate. This is interstellar space, not the space between planets, which is relatively crowded with solar wind and magnetic fields, but the true void between stars. A frontier so vast and empty that even light, traveling at its infinite speed, takes years to cross it. As we leave our solar system behind, preparing for the immense journey to Alpha Centauri, we must first understand what we are truly entering. What exists in this emptiness? Is it truly empty at all? The answer is both humbling and extraordinary. Interstellar space is not a perfect vacuum. It is filled, sparsely but measurably, with something called the interstellar medium. This cosmic substrate consists of gas, primarily hydrogen and helium, left over from the Big Bang, along with trace amounts of heavier elements forged in the hearts of ancient stars. Scattered throughout are grains of dust, microscopic particles no larger than smoke, drifting through the darkness like frozen whispers of worlds long destroyed. But to call this space, quote, zero is generous. The density of the interstellar medium averages about 1 atom per cubic centimetre. To put this in perspective, consider Earth's atmosphere at sea level, which contains approximately 30 billion trillion atoms in the same volume. Even the best laboratory vacuum on Earth, painstakingly created with sophisticated equipment, still contains millions of atoms per cubic centimetre. The emptiness of interstellar space is not just profound, it is almost incomprehensible. If we could gather all the matter in a cubic metre of interstellar space and compress it to the density of Earth's atmosphere, it would occupy a volume smaller than a single grain of sand. This is not emptiness as we experience it in our daily lives. This is a void so complete that matter becomes a rare and precious anomaly. Yet even in this near-perfect vacuum, forces persist. Magnetic fields thread through the interstellar medium like invisible rivers, stretching across light years, guiding the paths of charged particles and shaping the structure of the galaxy itself. These fields are unimaginably weak by earthly standards, millions of times fainter than a refrigerator magnet. Yet across the vast scales of interstellar space, they exert profound influence on the motion of matter and energy. Cosmic rays permeate this realm as well. High-energy particles, accelerated by supernova and other violent cosmic events, race through the void at nearly the speed of light. Some of these particles are protons, others are atomic nuclei stripped of their electrons, and a rare few are particles so energetic that scientists still debate their origins. These cosmic rays represent one of the primary hazards of interstellar travel. Unlike the relatively protected environment within our solar system, where the sun's magnetic field deflects many incoming particles, interstellar space offers no such shelter. A spacecraft journeying to Alpha Centauri would be constantly bombarded by radiation, requiring shielding far beyond anything used in missions to Mars or Jupiter. The temperature of interstellar space tells its own story. Without a nearby star to provide warmth, the interstellar medium hovers just a few degrees above absolute zero, around -270 degrees Celsius. Yet in certain regions, where shockwaves from stellar explosions have passed through, the gas can be heated to millions of degrees. This creates a paradox: space that is simultaneously frozen and scorching, depending on the energetic history of the atoms within it. What strikes us most profoundly about interstellar space is how fundamentally different it is from the space between planets. Within our solar system, we are always within the sun's domain. The solar wind, a continuous stream of charged particles flowing outward from the sun, fills the space around us. The sun's magnetic field extends billions of miles, creating a protective bubble called the heliosphere that shields us from much of the galaxy's radiation. Even at the orbit of Pluto, we are still within this solar cocoon. But as we journey toward Alpha Centauri, we must leave this protection behind. Somewhere beyond the orbit of Neptune, past the scattered disk of icy bodies, lies the Oort cloud, a vast spherical shell of comets that marks the outermost boundary of our solar system. This cloud, though never directly observed, is thought to extend nearly halfway to the nearest stars, reaching perhaps 1 light-year from the sun. Countless frozen remnants of our solar system's formation drift here in the darkness, bound loosely by the sun's gravity, waiting for perturbations that might send them falling inward to become the comets we occasionally see streaking across our skies. The Oort cloud is not a wall or a barrier. It is a gradual thinning, a fading of our sun's gravitational influence. To pass through it would take tens of thousands of years, even at the speeds of our fastest spacecraft. There would be no dramatic moment of crossing, no threshold where one could say with certainty, "Here the solar system ends and interstellar space begins." Instead, the transition is subtle, measured not in distance but in the slow weakening of the sun's grip on matter. Beyond the Oort cloud, we enter true interstellar space. Here, the sun is no longer a blazing disk in the sky, but a bright point of light, indistinguishable from other stars, save for its position. The heliosphere has faded behind us. The solar wind no longer reaches this far. We are now in the realm between realms, where no single star dominates, and where the galaxy itself becomes our environment. In this emptiness, distances lose their familiar meaning. A spacecraft drifting here could travel for centuries without encountering anything larger than a dust grain. The isolation is absolute. If something were to go wrong, if a system were to fail, there would be no possibility of rescue, no hope of return. The nearest worlds lie years behind and years ahead, separated by voids so vast that light itself seems slow. Yet this emptiness is not lifeless in the sense we might imagine. Interstellar space is the canvas upon which stars are born. Within certain regions, the gas and dust of the interstellar medium gather into vast molecular clouds, dense by interstellar standards, though still more empty than any vacuum on Earth. Over millions of years, gravity pulls these clouds together, compressing them until nuclear fusion ignites and a new star blazes into existence. The very atoms that drift in this void are the raw materials of future worlds, future suns, perhaps even future life. Some scientists have speculated about what else might exist in interstellar space. Could there be rogue planets, worlds ejected from their star systems, wandering the darkness between stars? Could there be objects we have not yet imagined, structures or phenomena that only reveal themselves across the immense scales of interstellar distances? The truth is, we do not know. Voyager 1, humanity's first emissary to interstellar space, has only just begun to sample this frontier, and its instruments will eventually fall silent, leaving vast reaches unexplored. To journey through interstellar space is to confront the universe at its most fundamental. This is not a realm of planets or stars, of solid ground or breathable air. This is space in its purest form, a medium where the laws of physics express themselves with stark clarity, uncluttered by the complexity of worlds. As we continue our journey toward Alpha Centauri, we carry with us the realization that the emptiness between stars is not merely an obstacle to overcome. It is a reminder of how rare and precious matter truly is, how extraordinary it is that atoms should gather at all into planets, into life, into beings capable of contemplating their own existence. The void teaches patience, it teaches scale, and it teaches us that in a universe this vast, the journey itself becomes the destination. We have sent messengers into the void, machines that carry our hopes across impossible distances. But how fast are these travelers truly moving? And what does their speed mean when measured against the vastness between stars? As we contemplate the journey to Alpha Centauri, we must first understand what humanity has already achieved. Our fastest spacecraft are marvels of engineering, accelerated to speeds that seem extraordinary by earthly standards. Yet when placed against the scale of interstellar space, their velocity becomes something else entirely. A profound reminder that the cosmos operates on scales we are only beginning to comprehend. Voyager 1, launched in 1977, holds the distinction of being humanity's most distant ambassador. It has travelled farther from Earth than any other human-made object, now more than 15 billion miles away, drifting through interstellar space beyond the influence of our sun's solar wind. It moves at approximately 38,000 miles per hour, a speed that seems breathtaking. If we could drive at highway speeds without stopping, it would take us over 650 years just to match the distance Voyager 1 has covered. This probe has been travelling for nearly half a century, carrying a golden record inscribed with sounds and images from Earth, a message to any intelligence that might one day find it floating in the darkness. Voyager 2, its twin, follows a different path through the outer solar system, but travels at similar speeds. Together, they represent humanity's first true journey into the space between stars. Not by design alone, but by persistence. They were not built to reach another star system, only to explore our own planetary neighbourhood. Yet now they drift onward, propelled by the momentum given to them decades ago, coasting through a void so empty that they will not encounter another star for tens of thousands of years. If Voyager 1 were pointed directly at Alpha Centauri, which it is not, it would take approximately 75,000 years to arrive. 75,000 years. To put that in perspective, 75,000 years ago, humanity had not yet developed agriculture. We were still nomadic, painting on cave walls, speaking in proto-languages that have long since vanished. The entire span of recorded human history would fit multiple times within the journey of Voyager to our nearest stellar neighbour, But Voyager is not our fastest spacecraft. That distinction belongs to the Parker Solar Probe, a mission designed not to escape the solar system, but to dive directly into the Sun's corona. Launched in 2018, Parker uses gravity assist from Venus to accelerate to astonishing speeds. At its closest approach to the Sun, it reaches velocities of 430,000 miles per hour, making it the fastest human-made object ever built. At this speed, one could travel from New York to Tokyo in less than a minute. It is so fast that if it could maintain this velocity and travel in a straight line toward Alpha Centauri, the journey would take roughly 6,700 years. 6,700 years. Still longer than all of recorded human civilization. Longer than the pyramids have stood. Longer than written language has existed. And yet, this represents the absolute upper limit of our current technology when operating under ideal conditions within the intense gravitational pull of the Sun. Then there is New Horizons, the spacecraft that gave us our first close-up images of Pluto. Launched in 2006, it is one of the fastest spacecraft to leave Earth's orbit, traveling at around 36,000 miles per hour. It reached Jupiter in just over a year and arrived at Pluto 9 years after launch, covering a distance of over 3 billion miles. After its encounter with Pluto, it continued deeper into the Kuiper Belt, studying distant icy objects that orbit in the twilight region of our solar system. Like Voyager before it, New Horizons is now on an escape trajectory from the Sun, destined to wander the galaxy for eons. If New Horizons were aimed at Alpha Centauri, it would arrive in approximately 78,000 years. The spacecraft that gave us breathtaking images of distant frozen worlds in less than a decade would need nearly 80 millennia to reach the next star over. The mathematics are humbling, the reality sobering. Why is it so difficult to go faster? The answer lies in the fundamental physics of propulsion and energy. Every spacecraft we have ever launched relies on the principle of action and reaction. To move forward, we must expel mass in the opposite direction. Chemical rockets, the kind that launch our spacecraft from Earth, burn fuel to produce thrust. But fuel has mass, and the more fuel you carry, the heavier your spacecraft becomes, requiring even more fuel to accelerate. This is known as the tyranny of the rocket equation, a mathematical barrier that makes interstellar travel with conventional propulsion essentially impossible. Even our fastest probes achieve their speeds not through continuous thrust, but through careful choreography with gravity. Parker Solar Probe uses the Sun's immense gravitational pull. Voyager and New Horizons used gravity assists from Jupiter, stealing a tiny fraction of the planet's orbital momentum to accelerate themselves. These maneuvers are brilliant, efficient, and elegant, but they only work within our solar system, where massive planets can serve as cosmic accelerators. To reach another star, we would need something fundamentally different: continuous acceleration over years or decades. An energy source so powerful and so efficient that it could propel a spacecraft to a significant fraction of the speed of light. And here we encounter another challenge. At extreme velocities, even a grain of dust becomes a devastating projectile. Interstellar space, while mostly empty, is not perfectly empty. Colliding with a particle the size of a sand grain at half the speed of light would release as much energy as several kilograms of TNT. Shielding becomes not just important but essential for survival. The energy requirements are staggering beyond comprehension. To accelerate even a modest spacecraft to 10% the speed of light would require energy equivalent to all the power generated by human civilization over several years, focused into a single propulsion system. And this is only acceleration. To slow down at the destination would require an equal amount of energy, unless we are content to fly past our target at relativistic speeds, gathering data for mere hours before vanishing into the void beyond. Our fastest spacecraft, then, are not merely slow by interstellar standards. They are effectively stationary. They drift rather than travel, coast rather than journey. The distances between stars are so vast that even our most impressive achievements in speed become invisible against the cosmic backdrop. A spacecraft moving at 400,000 miles per hour is still crawling compared to the span of light years. Yet there is something profound in the attempt. Voyager continues to transmit data from beyond the edge of our solar system. Parker's solar probe endures temperatures that would vaporize most materials, all to understand our sun. New Horizons revealed worlds we had only imagined. These missions teach us not just about the planets, but about patience, precision, and the long view of exploration. The journey to Alpha Centauri with current technology is measured not in human lifetimes, but in epochs. It would span the rise and fall of civilizations, the evolution of languages, perhaps even the biological evolution of our species. To reach the stars, we must first accept that our current spacecraft, as magnificent as they are, were never designed for such journeys. They are pioneers of a different kind, proving that we can leave our cradle, that we can touch the darkness beyond, even if we cannot yet cross it. And perhaps that is enough for now, to know where we stand, to understand the true scale of the challenge ahead, to recognize that the gap between worlds is not just distance, but time itself, stretched across the void like a bridge we have only begun to imagine building. Somewhere above a quiet desert, on a night when the stars rise sharp and steady, an idea takes shape that feels less like technology and more like magic. No towering rocket, no plume of fire, just a wafer of material no larger than your hand, and a beam of light so intense it could outshine the surface of the sun. This is Breakthrough Starshot. Not a spaceship in the way we've always imagined them, but a fleet of ghosts, gram-scale probes riding on sails thinner than a human hair, pushed not by fuel, but by photons. Tiny machines flung toward Alpha Centauri at a significant fraction of the speed of light. To understand why this idea is so radical, we must first let go of the familiar image of interstellar travel. There is no room for astronauts here, no spacious cabins, no spinning habitats. A Starshot starchip is closer to a postage stamp than a starship. A tiny printed circuit board, a camera measured in millimeters, a radio system smaller than a coin, all attached to a sail that unfolds like gossamer glass. The engine is not on board. It is at home. On Earth, an array of lasers, thousands, perhaps millions of individual beams, would lock onto a single sail high above the atmosphere. For a few minutes, the sky would ignite with invisible power, pouring gigawatts, maybe even terawatts, of energy into a square of reflective material no thicker than a whisper. To us, it would be silent. To the sail, it would be a hurricane of light. This is the strange secret of Breakthrough Starshot. Light, which has no mass, can still push. Every photon carries momentum. When it bounces off a reflective surface, it transfers a tiny kick. On Earth, that force is insignificant, lost in the noise of air and gravity. But in space, with a sail large enough and light intense enough, these single delicate nudges add up. Over the first moments of the laser firing, that tiny craft would go from drifting to racing, from walking speed to highway speed, then faster than a rifle bullet, then faster still. Within minutes, if the design works as intended, it could reach 20% the speed of light. 0.2 c. At that velocity, Alpha Centauri is no longer a 1,000-year dream. It becomes a 20-year voyage. Yet between the concept and the reality stands a tower of engineering challenges so tall it almost becomes its own cosmic distance, not in miles, but in orders of magnitude. The first challenge is the lighthouse itself, the laser array. To push a fragile sail without vaporizing it, the beam must be extraordinarily powerful and exquisitely controlled. We are talking about a phased array of lasers spanning kilometers of desert or mountaintop, all firing in perfect synchrony. Each individual beam must overlap and interfere in such a way that, from the point of view of the sail, it behaves like a single, coherent blast. If the focus drifts by even a fraction of a degree, the sail could tumble. If the sail tumbles, the beam misses. And without the beam, the starship becomes just another speck of debris, coasting slowly away from home. The optics alone are a puzzle of staggering complexity. How do we hold a beam steady on a target thousands of kilometers away, moving tens of thousands of meters per second in an atmosphere that shimmers and distorts like heat over desert sand? Adaptive optics, the same technology that sharpens our telescopes, must be pushed to extremes, correcting turbulence in real time with microscopic precision. Then there is the sail itself. It must be almost perfectly reflective at the laser's wavelength, or it will overheat and burn. It must be incredibly light, or the photons will not be able to accelerate it quickly enough. It must also be strong, able to survive a force equivalent to thousands of Gs of acceleration as the craft goes from stillness to relativistic speed in mere minutes. Engineers imagine materials sculpted at the nanoscale. Metamaterials with carefully tuned patterns that reflect nearly all incoming light, shedding heat like a mirage sheds form. A sail perhaps only a few hundred atoms thick, yet broad enough to catch the laser's intense glare. It sounds delicate, and it is. But in those frail layers lies the difference between centuries of travel and a human lifetime. Even if we could build the lasers and the sails, another, quieter problem waits, farther out. Communication. A Starshot probe would leave Earth's orbit, accelerate, and then drift in the darkness, unaided, for 20 years. No course corrections, no repairs, just a silent fall across 4.37 light-years of emptiness. By the time it screams through the Alpha Centauri system, it will have less than a day, perhaps only hours, within useful range of any planets. Its tiny cameras will snap frantic images at relativistic speeds. Its sensors will taste the stellar wind of another sun. And then, like a stone thrown through a distant window, it will keep going, never to return. All the science, all the images, all the proof that we have truly reached another star must fit into a signal transmitted by a radio no more powerful than a child's flashlight, from more than 4 light-years away. To be heard across that abyss, the probe must use its sail again, this time as an antenna or a reflector, shaping a narrow beam of information back toward Earth. On our side, vast receiving arrays, perhaps hundreds of dishes linked together, will strain to detect a whisper buried in cosmic noise. Minutes of transmission, years of waiting. Even at light speed, the data will take over 4 years to arrive. A snapshot of a moment that happened long ago, crossing the void to meet a humanity that may already have changed. And then there is the universe itself, indifferent and full of hazards. At 20% the speed of light, the interstellar medium stops being a gentle mist and becomes more like shrapnel. A collision with a grain of dust could release energy equivalent to an explosion. A single fleck of rock, invisible, could tear a hole in the star chip, rip off instruments, or destroy it entirely. Designers imagine layered shields, self-healing materials, or perhaps a swarm of probes instead of one, 1,000 tiny explorers sent in the hope that a few survive the journey. So where are we now in this ambitious dream? Breakthrough Starshot is at the moment a concept study backed by private funding and guided by teams of scientists and engineers. Early work is being done on advanced sails, on miniature electronics, and on the physics of laser propulsion. Small-scale experiments with light sails in Earth orbit and vacuum chambers hint at what might be possible. But the full laser array does not exist. The infrastructure, the energy, the atmospheric correction systems, these are projects measured in decades and in international cooperation. Some researchers are optimistic that a test flight to a much closer target, like the outer planets, could happen within this century. Others caution that unforeseen challenges may delay such missions far longer, yet the timelines, while uncertain, tell us something profound about scale. When we say 20 years to Alpha Centauri, it sounds almost modest compared to the eternity of space. A single generation, a human career. Someone who watches the launch as a child could, in principle, see the first images return in adulthood. But hidden inside that short-sounding number is the enormity of the task. To make that 20-year journey possible, we must coordinate a planetary-scale effort, harness energies rivaling small nations, invent new materials, and miniaturize an interstellar spacecraft into something we could almost lose between our fingers. The distance to Alpha Centauri has not changed. It is still 4.37 light-years, still more than 25 trillion miles. What projects like Breakthrough Starshot reveal is that to cross such a gulf in a single lifetime, we must bend everything else instead. Our technology, our patience, our sense of what a ship even is. Interstellar travel stops being a story of grand vessels and becomes a story of precision, of fragility, of information sent ahead of us like a message in a bottle. If one day a grain-sized probe does streak past Proxima Centauri b, capturing the first close-up glimpse of an alien world bathed in the light of a red dwarf, it will not erase the vastness between. It will illuminate it. It will show us, in the faint images and sparse data that trickle home, just how far we truly had to reach. Breakthrough. Starshot is a dream built out of hard numbers and harder engineering. Whether it succeeds or not, it changes the way we think. It tells us that the stars are not simply far. They are so far that even light, the fastest thing in the universe, takes years to make the crossing. And that to chase that light, we must reshape our imagination to match the true scale of the cosmos. In 2016, a quiet announcement rippled through the world of astronomy and then exploded into headlines. Not a new moon, not another gas giant, but something far more personal. Orbiting Proxima Centauri, the faint red companion to Alpha Centauri, scientists had found a rocky world. Not just any world, but one roughly the size of Earth, at a distance from its star where liquid water could, in theory, exist. For the first time in human history, the phrase potentially habitable planet was not an abstract idea scattered somewhere in the Milky Way. It had an address, just over 4.2 light-years away. Proxima Centauri b. The discovery was not made through images, but through tiny wobbles. Using the radial velocity method, astronomers measured how Proxima Centauri moved, back and forth, almost imperceptibly, as an unseen planet tugged on it. The signal was faint, buried in stellar noise, but persistent. After years of observation, the pattern became clear. A planet, at least 1.2 times the mass of Earth, completing an orbit every 11 days. Close, compact, suspiciously comfortable in what we like to call the habitable zone. The term habitable zone can feel almost magical, as if crossing into this invisible ring around a star guarantees oceans, blue skies, and continents washed by gentle rain. In reality, it is much simpler and much harsher. The habitable zone is just the region where a planet, given the right atmosphere, could maintain liquid water on its surface. Too close to the star, and water boils away into space. Too far, and it freezes into permanent ice. Proxima b orbits its star at a distance just 5% of the Earth-Sun separation, so close that it would fit comfortably deep inside the orbit of Mercury. But Proxima Centauri is a red dwarf, a star dimmer and cooler than our Sun. At that distance, the energy Proxima b receives is comparable to the sunlight Earth enjoys. On paper, it sits in the right place, the Goldilocks zone, not too hot, not too cold. Yet, as with so many things in the cosmos, the numbers alone do not tell the whole story. Proxima Centauri is not a calm, stable sun. It is a flare star, a restless ember that erupts without warning. Violent flares of ultraviolet and X-ray radiation surge outward, bathing the space around it in energetic storms. For a planet nestled so close, these outbursts are not distant fireworks. They are atmospheric events. Over millions or billions of years, such constant bombardment may strip away protective layers of gas, molecule by molecule, exposing the surface to raw space. Then there is the matter of time. Orbiting so near to its star, Proxima b is almost certainly tidally locked, just as the Moon is to Earth. One side of the planet would face eternal day, locked forever beneath a red sun that never sets. The other side would lie in perpetual night, a hemisphere plunged into endless darkness where starlight never rises. On such a world, the idea of sunrise and sunset may not exist at all, replaced instead by a permanent boundary, the terminator, where day meets night in a never-ending twilight. What would it actually feel like to stand on such a planet, if one could stand there at all? Imagine standing near the terminator line, where the sky is a deep, permanent dusk, painted in shades of crimson and violet by a red dwarf star hanging low on the horizon. The sun would appear larger than our own, but far dimmer, casting a muted glow instead of a bright blue day. Above you, stars might already be visible, even as the star of that system hangs in the sky. To one side, the daylight hemisphere, scorched and bright. To the other, the night side, cold and frozen, perhaps cloaked in ice. If Proxima b possesses a thick atmosphere, winds could howl constantly across that twilight band, transporting heat from the day side to the night side in a ceaseless circulation. Storms might build along the boundary between hot and cold, massive systems that never move east or west, only intensify and fade in place. Oceans, if they exist, might gather around this eternal ring of habitability. Liquid water clinging to a narrow band around the planet, while ice grips the dark and rock bakes beneath the red glare. But each of these scenes is a story we tell based on equations and models, not photographs. We don't yet know if Proxima b ever held onto an atmosphere, or if it was stripped bare long ago. We don't know if its surface is cracked basalt, a global ocean, or a frozen airless desert. Proxima b lives at the knife's edge between possibility and emptiness. It may be our closest potential second Earth, or our closest reminder that habitability on paper does not guarantee a world filled with life. This is where the story becomes both tantalizing and humbling. The word potential carries immense weight. It fuels missions, proposals, and late-night conversations in observatories and laboratories around the world. Some simulations suggest that if Proxima b started with a thick atmosphere and perhaps a magnetic field, it could have survived the stellar onslaught and still retain a blanket of air. Others argue that the constant flaring and early violent history of the star would have scoured away these defenses, leaving behind a rocky husk. In this uncertainty, something profound emerges. Proxima b is not just a candidate for life, it is a test for our understanding of how planets survive in the harsh light of red dwarfs. There are hundreds of billions of such stars in our galaxy, and many of the exoplanets we discover orbit them. If life can endure there, then the universe may be teeming with biology under dim red skies. If it cannot, then many of the most common planetary systems in the Milky Way might be more silent than we hope. And Proxima b may not even be alone. Hints of additional planets in the Proxima system have emerged. Objects that might be more distant, colder, perhaps encased in ice. Meanwhile, the brighter pair of stars, Alpha Centauri A and B, may also harbour their own planetary families. Observations have suggested possible worlds or debris belts there, though none have yet been confirmed in the same decisive way as Proxima b. Still, the suspicion lingers that the entire Alpha Centauri system may be an archipelago of worlds just beyond our reach, each with its own climate, its own story, its own relationship to its parent star. Why are we so drawn to this system, to this single planet circling a dim red sun? Part of the answer is proximity. Proxima b is not simply another data point in a catalogue. It is the nearest known exoplanet to Earth. If we ever build starships, if we ever send probes beyond the reach of our sun, this will almost certainly be among the first destinations. Its presence turns Alpha Centauri from a distant curiosity into a tangible goal. It transforms a vague someday into a specific target hanging in the sky. But there is another, quieter reason. Proxima b sits at the intersection of our hopes and our limits. It is close enough to imagine, but too far to visit with today's technology. It is plausible enough to dream of oceans and atmospheres, yet hostile enough to remind us that nature does not arrange itself for our comfort. It forces us to confront the gap between what we want to find and what might actually be there. In the darkness of your room, listening to these words, Proxima Centauri is just another point of light, usually invisible to the naked eye, buried in the southern sky. Around that faint star, an unseen world circles every 11 days, indifferent to our curiosity. Whether it is a second Earth or a sterile rock, it has already reshaped our understanding of the cosmos simply by existing. It has shown us that potentially habitable planets are not only possible, they can be right next door on a galactic scale. As we continue this journey through the Alpha Centauri system, Proxima b stands as both a beacon and a question mark. A nearby shore on the ocean between the stars, a reminder that the universe may hold other homes, but that reaching them will demand patience, ingenuity, and a willingness to accept that some of our most cherished dreams may meet realities stranger, harsher, and more complex than we expect. As we look toward Alpha Centauri, from the quiet outskirts of our own solar system, a strange realization settles in. With the rockets we have today, this journey is not just difficult, it is essentially impossible within a single human lifetime. Even our fastest probes, slingshotted by Jupiter and flung into the dark, would take tens of thousands of years to reach our nearest stars. To go farther, we must imagine engines we have never built and ships that are more like moving worlds than machines. We must step beyond the chemical flames of rockets and into a realm where the fuel is the same fire that powers the stars. Nuclear pulse propulsion, fusion drives, antimatter engines, vast generation ships drifting for centuries. These are not simple upgrades. They are changes in philosophy. They force us to ask not only, how could we go, but should we go this way at all? We begin with one of the boldest concepts ever seriously studied: nuclear pulse propulsion. The idea sounds like science fiction. Propel a spacecraft forward by detonating nuclear bombs behind it. In the 1960s, under a project called Orion, engineers envisioned a ship built like a floating fortress. At its rear, a massive steel pusher plate, cushioned by shock absorbers the size of buildings. The sequence is almost poetic in its violence. A small nuclear device is ejected into space. It detonates in an expanding sphere of incandescent plasma, and that blast slams into the pusher plate, jolting the ship forward. Then another device, and another. Hundreds, thousands. Each explosion a hammer blow, each hammer blow adding a tiny fraction of light speed. From the outside, such a journey would be a series of silent flashes in the dark, a starship riding a chain of artificial suns. But the raw physics is surprisingly generous. Calculations suggested that such a system, using nuclear fission or even fusion explosives, might accelerate a ship to 5 or even 10% the speed of light. At 0.1 c, the distance to Alpha Centauri no longer demands tens of thousands of years, but a few decades. A journey still longer than most careers, but not entirely beyond a single human life. Later, in the 1970s, the British Interplanetary Society imagined a gentler variant, Project Daedalus. Instead of discrete bombs, Daedalus would carry vast tanks of fusion fuel, helium-3 and deuterium, compressed and ignited in rapid pulsed fusion reactions behind the ship. No giant steel plate, no nuclear bombs, just an artificial star flickering, many times a second, at the tail of the craft. Daedalus was audacious in its detail, a 2-stage unmanned probe weighing tens of thousands of tons, accelerating for years until it skimmed along at about 12% the speed of light. At that speed, Alpha Centauri could be reached in roughly half a century of flight time, not instantaneous, not convenient, but something that could connect generations instead of geological epochs. Yet both Orion and Daedalus shared the same quiet obstacle. They relied on technologies we only partially understand, and on political permissions we may never grant. Orion's nuclear explosions would shatter any hope of a peaceful sky if launched from Earth. Daedalus needed helium-3 harvested from the atmospheres of gas giants, using industrial methods we have not yet built, to feed fusion reactors we have not yet mastered. Fusion rockets, in many ways, are the technology humanity almost has. On Earth, scientists already coax atomic nuclei together in magnetic cages and laser-driven implosions, trying to ignite the same reaction that burns in stellar cores. For now, these experiments consume more energy than they produce. They are laboratories, not engines. But if fusion can be tamed, even imperfectly, it offers an interstellar gift. Fusion fuel is dense in energy. A single kilogram of fusion fuel can release as much energy as millions of kilograms of chemical propellant. A fusion rocket would not need to carry oceans of fuel, only rivers. It would not need to burn all at once, only to whisper continuously, pushing a ship with gentle but relentless force until its speed reached a significant fraction of light. On this scale, thrust becomes less like an explosion and more like patience made visible. A fusion drive could accelerate for months or years, letting the ship slide into ever higher velocities, farther from the mental comfort of the slow orbits we know. Beyond fusion lies an even stranger possibility: antimatter, the mirror of ordinary matter. When a particle meets its antiparticle, they annihilate in a flash of pure energy. No ash, no smoke, just mass transformed directly into power. Antimatter propulsion dwells at the edge of our capabilities and our imagination. In theory, a gram of antimatter colliding with a gram of matter could release as much energy as a nuclear bomb. Captured, contained, and directed, that energy could drive a spacecraft with unimaginable efficiency. The fuel tanks could be tiny, the output enormous, speeds of 50, 70, perhaps even over 90% of light speed drift from fantasy toward rough calculation. But each step here is a chasm. We can create antimatter today, but only in quantities measured in atoms, at a cost that makes gold seem cheap. Containing it requires electromagnetic traps so perfect that no stray atom can ever touch the walls. A leak is not a stain or a spill, it is a micro-explosion. Still, antimatter is more than a science fiction trope. It is a promise written into the laws of physics themselves. There exists a way, at least on paper, to turn mass into thrust with almost perfect efficiency. Whether humanity will ever build a starship that hums with this annihilation, or whether antimatter will remain a laboratory curiosity, is a question for futures we have not yet earned. Even without exotic engines, there is another way to reach Alpha Centauri. Accept the slowness. Accept that the journey belongs not to individuals, but to lineages. Generation ships imagine humanity as a caravan, not a bullet. Enormous habitats spinning to create artificial gravity, containing forests, farms, rivers, and entire cultures. A ship in which children are born, grow old, and die, having never seen a planet, while their descendants inherit a mission begun centuries before. From the outside, a generation ship crossing interstellar space would be a dim, steady star, drifting almost imperceptibly against the background. Inside, it would feel much like a small world, seasons simulated, day and night controlled by lamps. History written not in years until arrival, but in the stories families tell about a world their ancestors came from and a world their descendants may one day touch. The challenge here is not only engineering, building life support systems that do not fail over hundreds of years, but psychology. How do you cultivate meaning in a society where no one alive was present at launch and no one alive will witness the destination? What does home mean when the only ground you have ever known is a hull a few meters thick between you and vacuum? In a sense, generation ships trade speed for continuity. They accept human time with all of its fragility and stretch it across the abyss like a bridge made from memories and promises. Yet if any of these advanced drives, fusion, antimatter, or others still unimagined, could push us to truly relativistic speeds, another subtle effect begins to shape the journey: time dilation. As a ship approaches a significant fraction of light speed, time on board slows relative to the universe outside. To the travelers, everything feels normal. Their hearts beat once per second. Their clocks tick with the same familiar rhythm. But to observers left behind around our sun, those hearts beat more slowly. Those clocks lag behind. At 90% the speed of light, time on the ship might pass about twice as slow as on Earth. A 10-year voyage, as measured by those aboard, might correspond to 20 years for those waiting at home. Push closer to 99%, and the effect becomes even more dramatic. The stars ahead grow blue-shifted and bright, the universe behind, reddened and dim. The travelers reach Alpha Centauri, while decades, perhaps centuries, have slipped by on Earth. In this sense, advanced propulsion does more than just shorten the trip. It fractures our shared timeline. The crew who arrives, may find a humanity older than they expected, transformed by technologies and events they never witnessed. To travel very fast between the stars is to become a sort of time traveler, not into the past, but into a future that outruns you as you chase it. All of these ideas, nuclear explosions pushing steel plates, fusion stars caged behind engine bells, annihilating antimatter and drifting world ships, are different answers to the same question. How do we cross a distance that laughs at our current speed? But hiding behind the equations is a quieter, more personal question. Would we even want to go? Not can we, in the narrow sense of technology, but should we, in the broader sense of meaning? Is it worth committing thousands of lives or harnessing the power of miniature suns and bombs to touch a star that will never notice we arrived? Some would say yes, without hesitation. That to step beyond our cradle is to honor every curiosity that ever looked up at the night sky. That even a single probe drifting among alien suns validates our restless drive to understand. Others might imagine a future where virtual realities are infinite, where telescopes can reconstruct distant worlds in staggering detail, and ask whether physically going is still necessary. Why risk generations in the dark when we can bring the universe, in exquisite high resolution, to our own doorstep? There may not be a single answer. Perhaps humanity will choose all paths at once. Unmanned fusion probes fired like needles into the void, slow generation ships carrying philosophical pilgrims, and deliberate patience as we build better telescopes and better dreams. What is clear is that Alpha Centauri is not just a star system. It is a mirror. When we ask how to reach it, we are really asking what kind of species we want to become, a species content to look, or one determined to touch. A species that measures time in election cycles, or in voyages that last longer than civilizations. Between us and that distant sun lie not only light years of emptiness, but possibilities. Engines that ignite like stars. Ships that live like ecosystems. Journeys where the destination is less important than the choice to depart. In the long quiet between pulses of propulsion and decades of interstellar night, a final truth remains. The decision to go will not be made by equations alone, but by whatever it is in us that hears the word impossible and quietly answers, not yet. We finally arrive. After years of travel in our imagination, and perhaps centuries in reality, we slip into the outskirts of the Alpha Centauri system. 3 suns share this sky. The warm golden light of Alpha Centauri A, the slightly dimmer glow of Alpha Centauri B, and far in the distance, the faint red ember of Proxima. Here, our own star is no longer the center of everything. It is just one more point of light in a sky already full of stars. If we stand, at least in thought, on a calm, airless platform orbiting Alpha Centauri A and turn our eyes toward home, what would we see? Our sun would not dominate the heavens. It would not blaze like it does from Earth, turning night into day. At 4.37 light-years away, the sun shrinks into a star of modest brightness. To the unaided eye, it would look like any other bright star in the sky. Nothing about it would announce, this one has oceans, forests, cities, and questions. Astronomers here, if they existed, would give it a name like we do. Perhaps a catalogue number, or a myth, or both. To them, our sun would not be the sun. It would simply be another G-type star, one among billions. But could they find Earth? Even from our vantage point, with our current instruments, detecting a small rocky world around a distant star is difficult. Planets do not shine with their own light. They only reflect the faint glow of their parent star. Earth is dwarfed by the brilliance of the Sun, outshone by a factor of 1 billion. From Alpha Centauri, the contrast would be even more unforgiving. If alien astronomers there had telescopes like ours today, Earth would be a challenge. With methods we use now, the way we hunt for exoplanets, what would we look like from their perspective? They might try the transit method, watching our sun and waiting to see if a planet passes in front of it, dimming its light by a tiny fraction. But geometry is not always kind. From most vantage points in the galaxy, Earth never crosses the face of the Sun. Only a thin slice of the cosmos lies in the right alignment to see our planet transit. Alpha Centauri does not sit perfectly in that slice. From there, Earth would not regularly eclipse its star. No neat little dips in starlight. No obvious signal that a small, watery world is there. They could try the radial velocity method, measuring the tiny gravitational tug that Earth exerts on the Sun, making it wobble ever so slightly. But Earth's pull is subtle, so subtle that even we, with some of the best instruments on Earth, are only now approaching the precision to detect Earth-like worlds around Sun-like stars many light-years away. Our own Sun, as seen from Alpha Centauri, would show little hints of motion, jiggling in response to Jupiter, Saturn, and the other giants far more than to Earth itself. Our planet's influence would be buried in a symphony of larger signals. To truly see Earth, they would likely need what we are only dreaming of now. Massive space telescopes with star shades or interferometers, instruments able to block out the blinding glare of the sun and isolate the whisper of reflected light from a world beside it. Then perhaps they could see us as we see our own pale blue dot. From there, Earth would not appear as a detailed globe with swirling clouds. It would be a single pixel, a tiny shifting point of bluish-white light, brightening and dimming as continents, oceans and clouds rotate in and out of view. No cities, no mountains. Just a changing colour, a flicker of reflected sunlight offering clues and questions. Even that 1 pixel, though, holds secrets. With sensitive instruments, they might notice that Earth's colour is not constant. It leans toward blue, yes, but with hints of green and white. They might see the signatures of oceans and land, of weather and storms. Breaking the light into a spectrum, a cosmic fingerprint, they could search for gases in our atmosphere. Oxygen, ozone, methane, water vapour. Taken together, these chemicals could suggest something remarkable. A planet out of equilibrium, where the air is constantly being reshaped by something active on the surface. Not proof of life, but a strong hint, a nudge from across 4.37 light-years whispering, this world is not dead. Yet still, Earth would remain small, impossibly small. The famous phrase, pale blue dot, would shrink even further. From Alpha Centauri, our home would not even be a dot you could point at with your finger. It would be a measurement on a graph, a number on a screen, a faint fluctuating line in an observatory's data archive. If they looked not with telescopes, but with radio antennas, what would they hear? Our earliest radio broadcasts, our first television signals, our primitive radar pings, they have been expanding outward in a sphere for about a century. That expanding shell has only just now reached the distance of a few hundred light-years, a tiny bubble in a galaxy 100,000 light-years across. Alpha Centauri, at only 4.37 light-years away, sits well inside this growing sphere of noise. In principle, a sufficiently sensitive radio telescope there could detect a faint, artificial hum from our planet, but it would not sound like a recognizable broadcast. Our signals disperse, they weaken. By the time they cross interstellar space, what began as a powerful transmission becomes a thin, nearly indistinguishable whisper, buried in the cosmic background. To pick out our radio leakage against the natural radio emissions of stars, gas clouds, and the galaxy itself would require technology far beyond what we currently possess. What would arrive at Alpha Centauri is not a clear song, but a soft, incoherent murmur, something that might appear as a slight excess of radio noise in a narrow band of frequencies. More recent intentional messages, targeted beams sent towards specific stars, are like needles in a cosmic haystack. They must be aimed precisely, timed exactly, and even then, they are fleeting. A few hours of carefully focused transmission, then silence. If you are not listening at the right time, in the right place, you will hear nothing at all. From Alpha Centauri's point of view, Earth is not a shining beacon. It is the faintest of hints. This is the humbling power of distance. Up close, our world feels enormous. Continents stretch beyond the horizon. Oceans seem endless. Civilizations rise and fall, each convinced of its importance. From orbit, Earth becomes a fragile, glowing marble. From the outer planets, a star-like speck near the Sun. From Alpha Centauri, even that speck dissolves into data. For anyone listening from there, we are not the center of the universe. We are, at best, a candidate, a maybe, a question worth pointing a telescope at and asking, is someone home? This perspective matters, not just philosophically, but scientifically. For the search for extraterrestrial intelligence, or SETI, our view from Alpha Centauri is a mirror. How hard would we be to find? How easily would our planet reveal its life, its technology, its struggles and stories? The answer is sobering and inspiring at once. We are difficult to detect. Our presence is subtle. That means that other civilizations, if they exist, may also be faint, quiet, and easy to miss. The absence of obvious signals does not mean we are alone. It may simply mean we are not yet listening with the right tools, in the right ways, or for long enough. It also means that every improvement we make, every new telescope, every new method of teasing a signal out of noise, has the potential to transform the sky. Worlds that were once just stars may reveal planets. Planets that were once just dots may reveal atmospheres. Atmospheres that were once just chemistry may reveal signs of life. From Alpha Centauri, Earth is a small, dim possibility. From Earth, Alpha Centauri's planets are the same. We look at each other across a gulf of light years, each side seeing for now only the barest outline of what might be. Standing in that imagined orbit around Alpha Centauri A, watching the faint sparkle of our sun among a million others, we are reminded of something quietly profound. Our significance does not come from our size, or our visibility, or our volume in the cosmic radio. It comes from our awareness. We are a species that can imagine this view, that can place itself there, looking back, reducing its home to a pixel and still finding meaning in it. That can understand that if we are so small from there, then every star we see tonight holds worlds that may feel just as large, just as important to someone else. In the end, the view from Alpha Centauri does not diminish Earth. It contextualizes it. It folds our bright, noisy civilization into the grand, dark canvas of interstellar space and asks us to see ourselves clearly, tiny, fragile, improbable, and yet capable of reaching, with our minds and one day, with our ships, across the light years. As our journey to Alpha Centauri comes to a close, we are left not with simple answers, but with a new sense of proportion. 4.37 light-years. A distance so often repeated, it begins to sound familiar, almost comfortable, like a number we think we understand. Yet behind that number hides a reality that resists comprehension. It is more than 25 trillion miles, a gulf so wide that our fastest probes would take tens of thousands of years to cross it. In the quiet of the night, that contradiction lingers. Alpha Centauri is our closest stellar neighbor, and it might as well be on the far side of forever. This is the strange beauty of proximity in space. On a cosmic map, Alpha Centauri sits right next door. On a human map, it lies beyond any journey we can make in a lifetime. We are close enough to measure its wobbling planets, to model its light, to imagine standing on the shores of Proxima B beneath a red sun. Yet we are still too slow, too fragile, too bound to chemical fire and patient engines to simply go there. In this tension between almost reachable and not yet possible, something important is revealed. The universe is not arranged around our convenience. It offers wonders, but not on our terms. Alpha Centauri, this triple star blazing faintly in our southern skies, becomes more than an astronomy topic. It is a mirror. It shows us what kind of species we are. We aim radio dishes across the dark to listen for whispers that may never come. We design missions like Breakthrough Starshot that may succeed, or may never leave the drawing board, but still push us to rethink what a ship even is. We talk about fusion drives, antimatter engines, and generation ships not merely as fantasies, but as possible chapters in a story that has not yet been written. Alpha Centauri is close enough to be a target, and because it is a target, it becomes a promise. Perhaps that is what this star system truly teaches us, that the universe is both unimaginably vast and surprisingly intimate. The same physical laws that govern fusion in its suns are at work in the atoms of your own body. The same light that left those stars years ago is entering your eyes now, carrying a silent record of where it has been. In that sense, we have already met Alpha Centauri. Its photons have already completed the journey. We are the ones still learning how to follow. The future of interstellar exploration will likely be slow, incremental, and uneven. There may not be a single first starship, but a series of attempts, tiny probes, failed launches, breakthroughs in materials, in power, in patience. Some ideas that sound impossible today may become ordinary. Others may remain forever out of reach. Yet history suggests that once a destination captures our collective imagination, we do not easily let it go. Alpha Centauri is now part of that shared mythos, a real place waiting across the dark, challenging us to grow into a civilization that can one day visit it in person. Until then, we explore with the tools we have: telescopes, simulations, radio waves, and imagination. Perhaps the greatest journey happens not in the spacecraft, but in the mind that dares to trace a path from this small, blue world to those distant suns. If this voyage through incomprehensible distance has kept you company tonight, you can gently support it. Tap the like button and let me know in the comments where you're listening from on this tiny planet. If you'd like to join us for more journeys through space and sleep, you can subscribe so you don't miss what comes next. And for those who want to go a little further, YouTube membership is available as an optional way to support the channel. Never required, always appreciated. For now, let the scale be what it is: vast, humbling, and unfinished. Somewhere out there, Alpha Centauri shines, indifferent to our progress, patient beyond measure. We are the ones racing against time, learning, dreaming, building. One day, perhaps, a faint artificial star will rise in its sky, and someone there, or something, will wonder about the distant world that sent it. Until that day, we rest under our own stars, knowing that even if we cannot yet cross the gulf, we can still look up, still imagine, still take the first small steps toward an impossible distance.